Last time, we ended on a question left open. If a network has hidden layers, how do you take an error at the output and figure out which of thousands of internal weights actually caused it and by how much? For 17 years, nobody had a working answer. Then, in 1986, 3 researchers did: David Rumelhart, Geoffrey Hinton, and a mathematician named Ronald Williams. The algorithm they described has a name almost every AI system still runs on today: backpropagation. It isn't a footnote in the story. It's the specific piece of math that made training a multi-layer network possible at all. By the end of this video, you'll understand exactly how it works. No equations required.
Plain machine, AI in plain English. We're tracing the complete history, from the very first idea all the way to the present. Let's continue. To understand backpropagation, don't start with the network. Start with a factory line. Picture 3 stations in a row. Each one takes what the last station made, adjusts it slightly, and passes it forward. At the end, an inspector checks the finished product and says, "This is off by 2 centimeters." That's useful information, but it isn't precise enough. Nobody knows which station's adjustment caused the error or how much of it belongs to which station, so nobody knows exactly what to fix. Now imagine you could reverse the flow. Instead of the inspector's verdict stopping at the last station, it travels backward through each one in turn. At every station, the size of the correction is scaled to how much that particular station actually contributed to the final error. The last station, closest to the inspector, gets the clearest signal. The first station still gets a correction, just a smaller share of it, reduced by everything that correction passed through on its way back. That reversal is what a neural network does every time it trains. Data moves forward through the network's layers to produce a prediction. This is called the forward pass. A loss function then measures exactly how wrong that prediction was as a single number. From there, the error travels backward through the same layers, and at each one, every weight updates by an amount proportional to how much it actually contributed to the mistake. Forward, measure, then backward. That full sequence is backpropagation. This is the exact piece the 1969 argument left unanswered. Minsky and Papert showed that a single layer couldn't solve certain problems. They never proved that more layers wouldn't help, they simply had no way to train one. Backpropagation isn't a bigger network, it's the missing instruction manual for training the network that was already possible. Let's slow down and look at the forward pass and the loss function specifically, because both matter for what comes next. Say the network is looking at a photo and predicting whether it shows a cat or a dog. The image goes in as numbers, pixel values. Those numbers get multiplied by the weights in the first layer, combined and passed to the next layer, which does the same thing again, layer after layer, until a final prediction comes out, maybe 80% cat, 20% dog. If the image actually was a dog, the loss function compares that prediction to the correct answer and produces a single number representing how wrong the network was. A confident wrong answer produces a large loss. A tentative wrong answer produces a smaller one. This number is the entire signal the network has to learn from. It doesn't know which of its thousands of weights caused the mistake. It just knows in total how bad the mistake was. Researchers call this the credit assignment problem. Given one error at the end of a long chain of calculations, how do you assign the correct share of blame to every single weight that contributed to it, all the way back to the first layer?
Here's the part that seemed impossible for 17 years. The mathematical tool that solves credit assignment isn't new. It's the chain rule, a piece of calculus that's centuries old. It says that if one quantity affects a second, which affects a third, you can calculate the total effect of the first on the third by multiplying the effects at each individual step together. Apply that to a network. A weight in the first layer affects the value at the first layer, which affects the value at the second layer, and so on, all the way to the final prediction and the loss. The chain rule lets you calculate exactly how much a change in that one early weight would change the final loss by multiplying together the local effect at every layer it passes through. The problem was never the math. The problem was doing this efficiently for a real network, which might have thousands or millions of weights. Calculating each weight's contribution separately, from scratch, would take far too long to be practical. Backpropagation's actual insight is a shortcut. Run the calculation once backward, starting at the loss and moving toward the first layer, reusing intermediate results as you go instead of recalculating them for every single weight. One backward pass assigns a precise share of blame to every weight in the network simultaneously. Once every weight knows its share, training is simple. Nudge each one a small step in the direction that would have reduced the error, repeat across thousands of examples, and the weights gradually settle into values that make good predictions. That nudging step has its own name, gradient descent, but the direction and size of every nudge comes directly from what backpropagation calculated. In 1986, David Rumelhart, Geoffrey Hinton, and Ronald Williams published a paper demonstrating that this approach worked, not just in theory, but reliably on real multi-layer networks solving real problems. Williams brought the piece the other two needed, a rigorous mathematical treatment of exactly how the backward calculation should work layer by layer, so it could be trusted to scale beyond toy examples. The paper didn't invent the chain rule. It didn't even invent the idea of applying it to networks. Versions of the concept had surfaced before, in scattered and mostly unnoticed forms. What Rumelhart, Hinton, and Williams did was make the case unmistakably. They showed multi-layer networks learning things a single layer provably couldn't, using nothing but forward passes, a loss function, and this one backward calculation, repeated. That's what closes the loop from Video 9. The 1969 ceiling was real, but it was a ceiling on one specific architecture, not on the entire idea of learning from weights. Minsky and Papert were right about what a single layer could do. They were never in a position to rule out what many layers, trained properly, could do, because in 1969, nobody could train them. In 1986, that stopped being true. So, what does understanding backpropagation actually change about how you evaluate an AI system today? Two scenarios are worth working through. Scenario 1. A vendor tells you their model learned this automatically from data. That's backpropagation running underneath, but it's only ever optimizing one specific thing, whatever the loss function was actually set up to measure. If the loss function measures the wrong thing, or a proxy for what you actually care about, the network will become extremely good at that proxy and confidently wrong about the thing you assumed it was learning. The right question isn't whether the system learned, it's what precisely it was rewarded for getting right during training. Scenario 2. A team tells you their deep network stopped improving partway through training, even with more data. This is a real, well-documented consequence of backpropagation's own mechanism. The error signal shrinks a little at every layer it passes backward through. That's built into how the chain rule multiplies effects together. In a very deep network, by the time that signal reaches the earliest layers, it can shrink to almost nothing. Those layers barely update at all. This has a name, the vanishing gradient problem, and it's a direct mechanical consequence of what you just learned, not a mysterious failure. Both scenarios point at the same underlying diagnostic. A learned system's behavior is entirely a function of what it was trained to minimize and how that error actually propagates backward through its architecture. Zoom out, and the full arc becomes visible. 1958, Rosenblatt's Perceptron, a single layer, genuinely limited. 1969, Minsky and Papert prove that limitation with rigor, and the field reads it as a verdict on the whole idea. 17 years of near silence. 1986, Rumelhart, Hinton, and Williams showed that the limitation was local to one layer and hand the field a precise, efficient way to train as many layers as you want. That's not a footnote in AI history, it's the mechanism. Nearly every network trained since, the ones behind translation, image recognition, and the language models making headlines right now, updates its weights using some version of this same backward calculation. Here's the 4-line version. Backpropagation didn't teach a neural network what to think. It taught the network how to blame itself correctly, tracing an error backward layer by layer until every single weight knew exactly how much of the mistake was its fault. Act 3 continues. The architecture can finally learn at scale. Backpropagation solved how to train a network. It didn't solve 2 other problems that turned out to matter just as much: what to actually train a network on, and how big a network could practically get before training it became too slow to be useful. Both stayed open questions for decades. In the next video, we jump forward to 2012, to a single dataset that changed the trajectory of the entire field, and the moment researchers realized the architecture wasn't the bottleneck anymore. That's video number 11, the ImageNet moment. Subscribe if you want the full arc. Each video in this series builds on the last. The AI glossary is in the description. 30 terms, plain English, free. This is Plain Machine. Thanks for watching.